Hello and welcome back. My name is Brian. I'm going to do some hacking on Tiger Beetle tonight. If you haven't joined us before, the project we're doing on this stream is to create a Rust client for the Tiger Beetle financial database. Tiger Beetle is a high-performance database, and it's got clients for several languages, including Node, Go, Java, and soon to be Python, I believe, but not for Rust. And occasionally people want to use Tiger Beetle with Rust applications. So on this stream, we're building a Rust client for Tiger Beetle front to back. If you follow this stream, you will see the complete creation of this Rust crate all the way from the beginning, all the way to the end, mistakes and all. And there are so many mistakes, so you're in for a mistake-filled treat. Let's see, what do we want to do tonight? I got specific plans for tonight, and first, I'll say a few things about, what we've accomplished over the last few streams. I think this is stream number 4. So let's go to our notes, because I'm starting to take some notes about this project. And if we review our notes, that'll refresh our memory on what we're going to do and what we've been doing. So in our notes for this project, I'm keeping track of everything we've done every episode. This is going to be episode 5. So far, we've set up this Rust crate and kind of looked at our underlying C ABI that we're binding to, because every Tiger Beetle client so far is made of bindings to a single underlying library written in Zig. And this library exposes a very simple C API that handles all the real work of interacting over the network with Tiger Beetle. And to start with in Rust, we're doing the same thing. We're just going to create bindings to what's called the TB client library written in Zig, and kind of just wrap that in an idiomatic Rust async API. In the future, we probably will go ahead and write another Rust client in pure Rust for mostly performance reasons, because there are some performance inefficiencies that are probably going to be inevitable with the binding to the C library. And I started off on this project on episode 1, kind of ambitiously sketching out a Rust API trait that I thought we would use to implement both clients, the Rust client and the bindings to the Zig client. And that quickly turned out to be a huge mistake, because I just didn't understand the Zig client well enough to know at all what I'm doing. So the next episode, we made some bindgen. We used Rust bindgen to create Rust definitions of the C API. Bindgen is a Rust tool that just looks at some C header files and outputs compatible Rust definitions. I don't often use bindgen. I never use bindgen, really. At least I haven't in a very long time. But it worked out really great for this project because Tiger Beetle defines a very simple C header that is intended for use by FFI, and that's very easy for bindgen to understand, and it worked out great. Normally, I would just write all those definitions by hand. The third episode, we just kind of, at that point, I realized I didn't know what I was doing. And so I just did some exploratory coding to understand how the client expects to be interacted with and how it behaves under various situations. At which point I felt like I understood enough to kind of start from scratch and try again to create a Rust abstraction and start filling it in. So that's what we did on the last episode of this stream. We sketched out a brand new API using a client here with a very simple impl with some methods, and the main method here being this async submit account lookup. Account lookup being one of the types of operations that Tiger Beetle supports. So our strategy here at this point is that we're going to create kind of our ideal Rust API that works with this one simple operation, the account lookup operation. And if we get that nailed down pretty well, we'll have a roadmap for implementing the other operations. And then sometime in the future, we will maybe go implement the full Rust version of this. But that's kind of like looking kind of distant at this point. We just got to get this working to start with. But it's kind of looking like clear sailing ahead at this point. We made a lot of progress last time. And this time, the thing I want to do, so we didn't finish implementing account lookup last time. We made a lot of progress. And in fact, we didn't run any code at all last time. I mentioned this several times on the previous stream, like, well, we haven't run any code yet. We've just run the type checker, which is, common in Rust. But we didn't run anything last time, and we didn't actually get far enough to fully implement account lookup, because right at the end of the last stream, I realized I had made a pretty big mistake around my assumptions for the unsafe pointers and their ownership, because this TB client API we're working on, it has a number of buffers that are passed back and forth between the Zig code and the Rust code. And so there's a lot of ownership to think about. Who owns those buffers when? And sometimes those buffers are allocated by Rust, sometimes they're allocated by Zig. And I realized right at the end that I made a pretty big mistake and I need to do some refactoring right away, because the code is just not sufficient. It's not sufficient to it is not sufficient to free pointers in all situations. I left open some potential leaks between times when the Rust owns the code and Rust hands those pointers. Rust owns some pointers, some heap allocations, hands those pointers off, and then gets them back, at which time it is again responsible for freeing those pointers. I left some situations open where those pointers could just get completely lost and never freed. So today, our main goal is to come up with a solution to ensure that those pointers are always accounted for. And when I say accounted for, I guess really means that anytime Rust sees those pointers, it has ownership of them and will be responsible for freeing them. So we're going to do in our notes. We're going to fix pointer ownership bugs, and then test account lookup ? We'll see if we get that far. I'm not sure. It's actually going to be kind of gnarly what we're doing today, but pretty typical Rust stuff, especially Rust FFI stuff. So should be an informative stream. I'm going to just commit my notes. And let's go back and think for one moment while I take a sip. Usually the first thing I do is kind of, every time I sit down and start a new coding session, is kind of catch up with where I was previously. Often I'll do a rebase of whatever branch I'm working on. But our last time working on this was only yesterday, so I think I'm just going to skip that and keep going where we are. But I am going to at least make sure I correctly built the C library we're binding to. And if you recall from previously, I don't have the build set up so that it builds both the static library, the TB client library, and the Rust bindings to it at the same time. So every time I change any Zig code, I have to remember to rebuild the Zig code, the real build.static library. So just to make sure, I'm going to do that right now. Oh, and interesting, it's building something. So maybe I changed something and I forgot about it. Usually it doesn't do anything like that. So I'm glad I built that at least. All right, and let's refresh ourselves on what we're gonna do. And I'll describe the problem again once I've once I've gathered my thoughts. And actually, before we get started, we can do a little housekeeping here. So I mentioned before that previously we had written some code and decided it wasn't good and we're going to start over. So all that code is down here in this old mod. And I think at this point we've caught up and our new code has caught up to the old code. So we can just throw this away. I'm done with this old mod. And in our main program, there's like a little test driver we've got. Doesn't do anything. We've also got some old code here. And I think, again, none of this really is going to have any effect on us anymore. Let's just dump all that old code and see if we can type check again. Okay. Now we're at a nice clean starting point. All right, and let's refresh each other's memory about what we're doing here. So in submit account lookup, this is a request to Tiger Beetle. And on the underlying Tiger Beetle API, if we go look in tbclient.h, there's a submit function somewhere, tbclient submit. And in the C client, this is polymorphic. You call this for every possible type of request. But in the Rust client, we're just going to have, a single function per request or per operation in Tiger Beetle terms. We make a request to the server and submit the server on operation. And so we're just working on this account lookup. And the way Tiger Beetle works is when you call submit, nothing happens pretty much. That is just in-queued infallibly. There's no possible error on submit. But then in the future, if we look at, let me find the right code here. Not that, that's not the right code. In the future, Tiger Beetle will call us back on some thread where Tiger Beetle client is actually running and call this function. So this is the completion function. So every time we call submit, at some point in the future on some other thread, we get a completion callback. And our strategy for Rust, because in Rust, we're going to be writing an async client. So that basically means it runs on a single thread, but asynchronously. You can submit lots and lots of stuff, and then in the future, on that same thread, you can await the futures of those submissions, those requests and operations. But it all happens on one thread, basically. In Rust, you can do async work in a multi-threaded way, but it's very hard to think about, and it doesn't really make a lot of sense. So our assumption right here is we have one thread where we're doing our async IO work in Rust. And so we're going to be submitting packets to TB client right here. And then they're going to be calling our callback with this completion callback in another thread. And our goal is to immediately get out of that other thread where the TB client work happened and get back into our Rust async thread where our Rust stuff is happening. Because that's where we're comfortable. We want to be in the async Rust runtime, not in this random thread that is, who knows the context of that thread. And the obvious way to do that is to just send a message immediately on completion back to the original async thread. So that's what we do. We create what's called a channel in Rust here, and we stuff that channel into our user data in our Tiger Beetle packet. This user data, we believe, is a pointer to something for us to use. This is very typical in FFIs, that they give you some way to access, some other data of your own, especially callback-based FFIs, because the callback itself has to be just a native function with no associated context. It's not a closure. And then you have some user data that the callback can use to kind of associate data with your function. And so what we've done is we put a channel sender into this user data, and then in our onCompletion callback, we just immediately, we're not doing this yet because I realized we made a bug, we send all this data right back over to the Rust async function. And then Rust, just says it submits the data, and then it waits for that message back that something has happened somewhere else in the world to process that request. And this code here is just kind of dealing with that processing. And this is all written, and this all looks about correct. Now, the big problem here has to do with pointer ownership. As you can see, we're putting a bunch of stuff on the heap. This is the boxes here. This packet that we are sending to Tiger Beetle client is on the heap. This account, this is the payload for the TB, the account lookup operation. Account gets stuffed into the data here. Every operation has some operation specific payload. And then this message sender is also boxed. So all this stuff gets stuffed on the heap. And at this point in execution right here where I've highlighted, it's all owned by Rust. And because it's in this owned box, it's guaranteed to be destructed by Rust at some point in the future. And this is all going to get, this is an async function, right? So everything here is going to get captured into a future because it's all async, especially after this await point here. Everything after this is going to be happening in some kind of future. So it all gets rolled up into a future and passed back and then executes at some time in the future. So here, the idea here was these things are owned by Rust. Here we say, turn these boxes into raw pointers, at which point they're kind of temporarily owned by nothing. There's no guarantee they will ever be freed. This data also converted from a box directly into a raw pointer. And then this box that contains the packet also converted into a raw pointer. And that's not the same as taking a raw pointer. We're not taking an unsafe pointer to these boxes. We are taking these boxes and converting them into raw pointers. They're no longer Rust boxes. And then down here, after we get this message back from Tiger Beetle, or the called back on another thread by Tiger Beetle, then we do the exact opposite. We convert them from raw pointers back into boxes. So after these are all reboxed, at that point, they are good to destroy. Rust will guarantee they'll get destroyed at some point in the future. But from this moment in time right here until this moment in time right here, nothing is promising to destroy these boxes. And that seemed okay when I wrote this, except if we think about what happens here. So this await point, when we call await here, it's going to take this future, and the way async await is it automatically creates futures out of your stack for you. And all the state on this stack is going to get packaged up into a struct. And that struct is going to get passed back up the stack to the caller. And then they just have a struct, a value that is a future that can be used to go wait on this other thing and continue running this code. But this does not ever have to execute again. Like after this point, there's no guarantee this code ever executes. So if this code never executes, these boxes never get reconstructed, these values on the heap never get freed, and we have a memory leak. So big mess. There's also another subtler case where we have a channel here, and this channel doesn't actually have to be read. So maybe this future is run, and maybe though this channel doesn't actually get read for some reason. Maybe there's a panic right here. There obviously isn't today, but there could be at some point. That channel could get discarded without ever reading the message off the channel. It's the same basic issue though. We have an unsafe pointer that is supposed to be owned by Rust, but it's just kind of floating out in the ether, and there's no opportunity to actually clean it because Rust doesn't know about it anymore. So, big mess. This is the kind of thing you have to think about though pretty hard when you're dealing with the interop between two languages, and in particular Rust and some CFFI. Now, another thing to point out here is that what you might want to do or think of doing, and what I originally did, was I did not convert these boxes into raw pointers. I just took a pointer to what's inside the boxes, which seems like, it might work, because then we still have these boxes in this future here. And when the future gets discarded, those boxes will get destroyed. But we actually can't do that because of aliasing rules. These boxes, aliasing rules is one reason we can't do it, but there are other reasons not to do it that way as well. These boxes tell Rust that, like, this code owns whatever is behind this pointer, and nobody else is going to even look behind those pointers. But that's not what's going to happen once we pass these pointers off to TB client. TB client is going to read and write the stuff behind those pointers. So once we call TB client submit, these boxes are just not allowed to exist. But there's another reason. Even if we put these in some kind of Rust owning type that could also share the interior pointer, we still probably don't want to do this, because what if this future we're looking at here gets destroyed before TB client is done munging this packet? In that case, we've got all kinds of problems. So really, this is a very clear ownership transfer. These pointers, once we hand them off to TB client, they are TB client's pointers, and we don't get to touch them again until after it calls us back. So there's a few ways we could think of approaching this. The obvious thing that we have to do is that in our callback, this is our completion callback. This is where we finally get access to those pointers again. Here, we need to immediately convert those pointers back into a Rust owned type, because the time between, if we're going to send a message back to the other thread, we immediately need these to be owned again, and Rust has to take responsibility for freeing these boxes. So what I was doing was I was mostly passing these pointers, raw pointers, right back to the other thread over a message. And that period when that message is in transit, nobody owns those pointers, and that's no good. So the thing we have to do is convert these pointers back into Rust boxes immediately, and then we can think about getting them back into the other thread. So an obvious thing to do would be to kind of mirror our submit account lookup code over here and like introspect this packet and say, is this an account lookup packet? And if it's an account lookup packet, then we do these unsafe conversions to the account lookup packet specific types, or the account lookup operation types, because every request we submit, every operation is going to have different types involved. And in that case, we'd probably have like a switch here. We'd have a switch statement or a switch expression on the packet type or the operation type represented by this packet. And then we might pick out like a account lookup message if it was an account lookup operation, and convert the user data back to a channel that can send an account lookup message, and do the same thing for every type of operation. And also probably your user data. This is operation specific. So again, in our type switch statement on completion, we convert that data into an account lookup operation, or a box of an account lookup operation. So we'd have our kind of type specific, operation specific logic spread into two different places. One in the submit methods and one in this kind of monolithic on completion method. And that's reasonable. I mean, it's not, you could do that perfectly reasonably. And it's a common thing to do. You might do that. I might do that. I'm not going to do that. I don't want to do that. I don't want to have the operations logic split into two different places. Even though this is a pretty small program and it's manageable. It's totally manageable. I don't want this on completion to have a big operation switch statement in it. What I want is for all the logic related to account lookup to live in this account lookup method or close to that account lookup method. So there's a few ways to do that. The way I'm going to do it is, there's so many trade-offs involved here. But the way I'm going to do it is something that's pretty common in Rust, and it's pretty cute and clever. Since instead of taking a message sender, a channel here, and putting that message sender into user data, I'm just going to stuff a closure into user data. And then on completion, that closure can be the same, have the exact same type for every submit operation. For every operation, this closure can just be completely opaque as far as the type conversions involved within. And then on completion, we'll just take that user data, unsafely convert it to a closure, and then call the closure and let the closure figure out all the type conversions and be responsible for sending the message back to the original thread. I know that was a lot of explanation. It'll all become clear, I think, pretty fast. So I think what I want to do here, here's our on completion. This is just a raw function. And this, I want to define the closure that we're going to stuff into this packet and the completion is going to call. And I'm just make a type def here. I'm going to say type on completion is equal box, because this is going to be a pointer that has a lifetime that is hard to reason about, so it's going to be on the heap. And it's going to be what's called a fun one in Rust, I believe. And the Rust closure type syntax is kind of funky, but it looks like this. There's multiple types of closure in Rust, but a fun one is a closure that can be called once. In this fun one, I am just going to give it all of this stuff. And then the closure can be responsible for figuring out what to do with this stuff. And then the closure, we can just write the closure over here, right next to the code that is responsible for dealing with account lookups. And there's lots of downsides here. I'm not going to really discuss them ahead of time, but we'll see them as they come up. And this will probably have to, as we implement more types of operations, we'll see there's a lot of boilerplate and redundancy, and we'll have to think about it. But this is a very cute, easy way to deal with this kind of contextless raw function callback in an FFI in Rust. You just immediately create a closure and let the closure do whatever it wants. The closure can just capture whatever its state it wants. So we have a box of a function, and this function, I think it is just literally going to have this type signature. And in the type definition of a Rust closure, I believe we can give the arguments names. but I'm not entirely sure. Let's give it a type check and see what it thinks of this. Well, it didn't like something I'm doing. Now you can't actually give these names. Not sure what I'm thinking of. So can't give these names. That's okay. We're not gonna. I wonder if I want to. It'll be obvious because this is gonna live forever right here. So I was thinking like maybe I should give these like commented out names, but now these closure definition and the corresponding function callback are gonna live right next to each other forever. Forever. All right, let's type check that. All right, I got the name of fun once wrong. Fun once, not fun one. Man, a real Rust expert would know that. And this has to be a dynamic trait object. In Rust, closures are traits, and there are multiple ways to handle dispatch with traits. You can have them handle dispatch dynamically or statically. In this case, this closure is going to be a dynamically dispatched closure. So we have to use this dyne keyword. Right, now that type checks. And here, I'm going to comment out this because I'm going to want to reference what I did here in the future 5 minutes from now, hopefully. I'm sorry, just windowing around and making sure the stream seems to be operating correctly. And actually, let me check my messages chat. All right, I'm okay. You have a little bit of a thing going on outside in the real world, and need to make sure nobody's sending me messages. Okay. Okay, so this on completion, this is just going to immediately say let fun underscore, fun's a keyword, so I can say fun underscore, say let callback equals, and I'm kind of referencing what I did here because we're extracting the user data again, but we are using different types now. Going to be a box from raw, and there's a whole lot of pointer dereferencing and coercion going on here. Very common, this type of dereferencing and coercion is very common in FFI code, but pretty unusual for Rust. And I think what I'm going to do is do this. I'm not going to put the box in this type def because right here I want to name that on completion type, but without the box. So this is a mutable pointer to an on completion. I think that's what I want. And the reason I have to put this in a box is because this dynamic fun once, this is a fat pointer, which I'm not going to go into, but all I have access to in the client API is a single pointer, a thin pointer that I can access and use for myself. But this is a fat pointer. That's why this has to be boxed. Just like a second layer of heap indirection. Okay, that looks like it might be correct. And then we say, oh, I missed something in there. Ah, there, probably that. Probably that. And then we just call back. Although, do I want to call that back? No, I want to do exactly what I did here and null out that pointer that I just converted into a box, just to make sure nobody else ever looks at this valid pointer. Now it's an invalid pointer. And now I'm going to call this callback with all the same arguments. Client, packet, timestamp, result pointer. Yep. Remember, I'm just calling a callback. I'm no longer sending a message. I'm letting the code from this thread just do something else, whatever it wants to over in this other thread. And that's super fun. I remember when I realized I could do that in Rust, I was like, you mean I can just write like a block of code here that looks kind of inline to this code, but it actually runs temporally way over there in some other place in some other thread, just because the closure will be wrapped up safely and punted out somewhere else. I was like, wow, that's powerful. So we call this callback and we're done. Don't want to do anything else here. I'm going to want to look at this code again. It's pretty simple, but I'm going to want to look at it again. All right, so this callback, I think that's the whole callback now. So the completion really does almost nothing now. It's just like, we're going to do whatever the other code wanted to do. Completion, get out of that completion as fast as possible. And I did something. What did I do wrong? Callback, this should be a box star mute on completion. Expected a fun once, found a C void. I'd expected this to be a fun once. I think I probably need to dereference this. No, that doesn't sound right. I have to dereference the packet to get that. The dynamic fun once. It's not implemented for C void. Star mute dynamic fun once. This is not an amazing error message, actually. Required for the cast from star mute C void to star mute whatever this is. Treat fun once. It's not implemented for C void, star mute, C void to star mute. Dynamic fun once. Did I do this incorrectly in some way? It might be. I'm going to put a type annotation here just to help me out a bit. This is a box of on completion. And let's think hard about this. I'm wondering if I did not use the right amount of indirection here. A box of dyne fun once. This might, what I'm thinking is this might have supposed to have been a box of dyne fun once. Might need, because if we put this dyne fun once is a fat pointer. If we put it in a box, that box is also a fat pointer. So to make a thin pointer out of it, you might have to double box it, which is super ugly. But also this down here, let's look at that error message again. What I'm trying to do is take that user data, which is a void pointer, and convert it into this pointer to fun once. And that is a fat pointer, so you definitely can't just do that. Expected fun once, found C void. Yeah, I think I basically did not include enough indirection here. And what I want to do is I want to put one box here. And then that might work. We'll see. Call to unsafe function. That's great. That's fine. Call to unsafe function is A-OK. Oh, there we go. I was right. I mean, I was wrong initially, but then I was correct about that double indirection. So as far as efficiency goes, this is kind of a big bummer because this callback is a box of a box. And that's one of the things we're going to run into as we go on with this project and the design that I've got here is we're going to have a lot of boxing. But we can rethink the efficiency of this later. And for now, let's get something working that is easy to understand. And even though this has got a boxy box, still probably the easiest way to understand this. Okay, now let's go back to our original, let's go back to the submit side, our Rust thread, and think about what we're doing there. And what we need is a closure. So we no longer need this completion message or this completion message channel. We'll probably need a different message type at some point. But for now, I'm going to say, we'll keep the channel around. We're going to need a channel still to get the data back across the thread. We just have to change this channel type. But we're going to say let completion, let callback equals box of a box, box of a box of a function. And here, this argument list is going to be gross. I'm just thinking, I'm slowing down because I'm thinking whether there's any way to syntactically make this pleasant. And here we got to say context. And I'm going to go ahead and put a type annotation here because this is going to be gross. It's a box of an on completion. And then the arguments are, let's go put this on another line. Context. Client. And I'm copying from over here on the other window. Client. Packet. Timestamp. Result pointer. Result len. And now, let's put a to-do here. And this isn't going to type check, I think, unless this type annotation maybe pulls all the way through this closure. We'll see. Oops, what did I do? Just trying to format this in a way that is not quite so hideous, but it's pretty gross. Box. There's that. Oh, that looks a little better. Okay, that's passable. Let's see if we can do that. No, that's not passable. Let's see if this type checks. I don't think so, yeah. Box. Oh, this syntax is wrong. You got to call a initializer or a constructor on the box. Oh, okay, that all type checks. Great. I was afraid we were going to have to annotate all these, but this is pretty ugly. Now, one of the big problems with the approach we're taking right now of just having a callback to deal with what used to be handled over here in the onCompletion method is that we're going to have to write the completion code in front of this code that actually submits the operation. And that is gross. But we'll do as little as possible here in the callback. And hopefully it won't be terrible. Again, all this callback, all we want to do in this callback is convert some unsafe pointers back into Rust boxes so they can be destroyed properly. And then we're going to punt them back to the main thread. All right, let's think about how to do that. So this the sender here, TX, we don't need down here anymore. We're going to capture it up here. I'll say let TX equals TX. We probably don't need to do this. It'll probably move on its own. I'm just putting this here just for readability for now, because we're going to capture this sender instead of sending it as an unsafe pointer. Now this user data, this now is no longer the message or the sender, it's the callback. And again, it's a pointer to a fat pointer of a callback. And at this point, nobody owns that callback. Callback is re-owned again immediately in the completion. And this completion is, I believe, guaranteed to always be called. Even if you close the client, this completion will be called. If you don't close the client, it won't be called, but then you've got other problems. I mean, if you leak the client without ever closing it. All right, so here in this callback, we're going to, this is a channel of completion message. And this completion message is defined over here. All right, let's first think about recovering those pointers. So in our original code over here, we got rid of that. We already did that. We did that. But this we need to go do again. So this code, we talked about this last time, but in this callback, this happens on some other thread. This result pointer is not owned by the Rust side of this equation. This result pointer is owned by the client. And as soon as this completion finishes, this result pointer, we can't touch it again. So we're copying it into a vector, a Rust vector. Because this, again, as soon as this callback here, this closure exits, the client is off doing something in the other thread, and we can't touch that pointer. So here we have result pointer and result len. That makes sense. And then we send the message, tx.send, and we send something. And typically send can return an error. In this case, with this particular channel, that error, it means that the receiver hung up. So it's very common in Rust to just say ignore a failure on send. Like if the receiver hanging up is a pretty standard thing. And if we think about what our options are if the receiver hangs up, there's not much we can do except we need to destruct all these pointers that we own again. Okay, so we're not going to actually send yet though, because we haven't done everything we need to do yet. We've taken this result and we've made it owned, or we've made our own version of the result that we own. Now it's time to solve the actual bug. We got to take those unsafe pointers and convert them back to Rust owned boxes. So here I'm going to say let packet equals box from raw packet. And I think we need to cast this packet as star mute tbc tb packet t. And at this point, Rust owns that packet allocation again. So there's no, once we get here, there's no chance that we're going to lose that packet. That packet is going to be deallocated at some point, as long as, well, as far as our code is concerned, this packet's going to get deallocated. And there's one other piece of allocated data here, and that is our called data in the packet field. This is our operation payload, and it's a U128 or a box of U128. And we're going to call that the payload box from raw packet. And I'm going to do this first before we convert the packet, and I'll show you why in a second. This packet as star mute U128, not packet, but packet dot data. And then along with this payload, and the reason I put the payload conversion into a box before the packet is because I want to go null out that payload field, that data field. I'm going to say packet, and we couldn't do that if there was a known pointer to it. I'm going to say packet dot data equals pointer null mute. I mean, we could also do it here through the packet owned box. And a note here, this is interesting. So here I've shadowed the unsafe packet. At this point, we have a safe packet, but we probably can't, we're not allowed to touch that unsafe packet. And by shadowing it, we made it literally impossible to touch that unsafe packet, which is one of the nice things about shadowing in Rust. A lot of people question whether shadowing is good or bad, but I have always found Rust shadowing especially to be very good. I'm not going to say I've never had a shadowing bug, but I find it very useful to shadow in Rust. So then we've nulled that packet data. And is there something else I needed to do here? We got the payload back. I want to make an assertion about the size of that payload. I'm going to say assert EQ. And we did the same assert. Actually, no, we didn't. Did we do that assert? I'm wondering if we did the assert down here. No, we asserted something else down here. The result, we made an assertion of the size. But we set this size here when we sent the packet. When we get the packet back, I want to make that a same assertion. I don't think the client is going to mutate this field at all, but I'm going to assert this thing that I believe that I know. Packet dot, this is wrong here. Parens in the wrong spot. And this syntax here looks super gross, but it's pretty rare. This has to do with the fact that, sorry about that. This has to do with the fact that packet at this point is an unsafe pointer to a struct. And if you get the syntax wrong, the compiler will tell you immediately you forgot to do this thing, this dereference with parens around the dereference. Pretty ugly though. A syntactic corner case in Rust. Packet.data size is stood mim. Now we already have mim imported. Mim size of U128. And then here we need to send something, but I want to just type check what we got and make sure we have got all this stuff seemingly correct. Mim size of, okay. This error is about a size mismatch between definitions in the FFI and definitions in Rust. This is kind of unfortunate. I kind of wonder whether the FFI could be a little more precise, but it might just be an artifact of C not being very precise about various things. I don't want to blame C for something. I'm just speculating. Anyway, the FFI defines this data size field as a U32, but Rust defines sizes of things as usize, which is correct. It's actually probably an artifact, actually not of C specifically, but just how Tiger Beetle has defined this, because there's no reason to have a packet size here, a payload size that doesn't fit into a U32. This could even be something smaller. But anyway, I'm just going to cast this here. What did I just do as usize? Okay, that should, oh gosh. I was going to say that should type check, but no. Did a bunch of unsafe stuff here and didn't put unsafe around it. And then hopefully this is the extent of the unsafety. This code is all responsible for doing unsafe casts. And then down here, you probably won't need anything unsafe for actually handling the response. That's not true. I'm wrong about that. Anyway, it's FFI code. There's lots of unsafety involved. This isn't normal Rust code. This is FFI code. Normal Rust code isn't this tough. All right, what am I doing here? Oh, still just type checking. Okay, now we type check. Now let's figure out about sending this transaction, this let tx t equals tx here. I'm going to put down here, and in fact, I'm not even going to put that here. I'm going to assume the capture works correctly. We need to capture this sender, right? This is our only capture. We're capturing this channel sender and then sending something over on it. And I don't remember offhand whether this will be moved into this closure or not. You know, the semantics for closures have changed subtly over the years. I don't exactly remember. Sometimes in the past, you've had to be very careful about whether things are captured by value or captured by reference. And we're going to send something here. And we already have a previously defined completion message. But we need more than that now. And let's go ahead and take this completion message, but turn it into something, turn it into the thing we're going to send right now. We're going to reuse this, but augmented it with the specific types we need for account lookup. So this packet is no longer unsafe. This is a box. So if this gets lost in transit, it'll be deallocated correctly. And we have our result here. And the other thing that we had to unbox was this result we haven't converted to an operation specific type yet. But this next thing is the payload. I'm going to say down here, these are all the arguments to onCompletion. After this, I'm going to say packet payload. This is something. This is specific type specific to the operation we're dealing with. So I am going to make that a type parameter here. And we'll call this P, actually. We could also call this payload, but it's kind of less common to put full words as type arguments in Rust. So we have a packet payload, and this is our payload here. And then when we send this, it's going to be, so now we know the type of this channel. It's a completion message of U128. So this is a completion message of the payload type. And again, this pattern is all going to have to be repeated for every type of operation. And the type specific stuff, the operation specific types, are the places where the duplication is going to be hard to deduplicate. You know, stuff like converting a packet from an unsafe pointer to a box, that can kind of be factored out very easily. But anything that is type specific, like this completion message of U128, this entire channel, the type of this whole channel is specific to the operation we're working on. And it's going to be hard to deduplicate that. But anyway, that's pretty far in the future at this point. So we're going to send a completion message with the context client packet timestamp result and payload. And let's see. We called this packet payload. I'm just thinking about whether to give this the same name in this local as in this field. Otherwise, we're going to have to say packet payload is payload. I'm kind of inclined to just say packet. So over here in this pane, packet payload seems pretty descriptive. Over here in this pane, saying packet payload seems kind of excessive. I'm just going to call it payload. I'm doubting myself immediately. Chat, I'm doubting myself immediately. This is not important. I'm going to call it payload everywhere. Let's see if that builds. Of course it does not. And payload, expected U128 found a box of U128. Okay. So originally the payload had to be a box. And then in this message, we're dealing with Rust reified generics. This payload doesn't have to be a box. We could unbox it right here, but that's just more code here that has to happen on the other thread. So I think we're just gonna send it back in its own box because we're honestly never gonna touch this payload again, probably. We're just holding on to it so that it can get destroyed somewhere. Is that true? We could destroy it on the completion thread if that is true. But it is not true because this is an allocation. And right now we're being very sloppy with allocations. But in general, I want to return allocations back to the original thread so maybe they can be reused in the future. Let's see that. So here we are there. Okay, box expected something. Packet star mute found box of something. Message.packet. What are we looking at here? I feel like this is something way down here. Okay, all this code is not correct anymore. 112. So this is already done. So when we receive this message is a completion message, and we don't have to do any of these unsafe conversions anymore. You can say let packet equals message.packet. Anything else we want to unpack from this message? Message result. Let result equals message.result. And this is so nice to be back in the realm of safe Rust again in this result handling code. Because we can just destructure this message and take our things back out and stop worrying about unsafe pointers. Status. Yep, message result is now just result. Try into, so I'm converting this message result into U128, which is the payload type. That's what I'm doing here. So right here, you can see I'm kind of like taking the things out of the message that I think I'm going to use here. And then I don't think there's any unsafety here anymore. Let's see if that proves true, which is very nice. But in some cases in the future, this is going to be an unsafe cast for other types of operation. But that's just converting a buffer into U128 is safe to do. Let's see what we got going on with our compiler. I made a syntax. And it builds. Whew. Okay, that feels pretty good. This is like what I wanted to accomplish today. And we got there pretty easily too. Feeling good about that. I'm wondering, what I'm thinking that now is, should I celebrate by taking a break or keep going? Because the next step is probably going to be running this code that we have spent 4 hours not running and doing a bunch of probably runtime debugging. But who knows? Maybe it'll just work. I doubt it. Also, we're going to need to write a little test harness with async code. So we're going to have to probably take Tokyo as a dependency and remember how to set up Tokyo. I think, chat, gosh, I hate to do this to you, chat, but I think I'm going to take a 5-minute break and step out, get a drink, take a breather, and kind of collect my thoughts about what we're going to do next. All right, I'll see you in a second. Sorry that took so long. Stuff happening over here. I better take a quick synth solo before we get started. That's enough synth solo. So what were we doing before we disappeared? All right, we finished our big goal for the day. That's great. Okay, so let's recap what we've accomplished and then what we're going to do next. Let's do it in the other order. Let's think about what we're going to do next, and then we'll kind of step back and make sure we've accomplished what we think we've accomplished. Nope. Let's just continue. We finished implementing the code for submitting an account lookup operation to Tiger Beetle. So at this point, we think that we've submitted the operation to the Tiger Beetle client and then handled the callback on another thread, safely converted our unsafe pointers back to Rust boxes, sent those pointers back to the main Rust thread, and then handled the result of the query. I think we've accomplished that, which has been our goal for 2 days now. So the next thing I want to do is actually run this code and see if it does the thing. And we've spent about 4.5 hours just writing the code and running the type checker to make sure it builds. And I think it looks good, but I don't know if it's correct. Don't know if it works. But at this point, we have this pattern here for one type of request. And if this works, we should be able to follow this pattern. Before we test it, I'm just going to read through it one more time and think about whether I did it all right. So this assertion, my assumption is that a 0 account ID is not a valid account ID. So I've asserted that here. Because later on, assuming that a 0 account means that the account wasn't found by the query. That's kind of the big assumption that I'm wondering whether we've screwed up, whether I've screwed up. You didn't screw up. You succeeded. You succeeded by being here with me tonight. All right, so we create a channel. Then we construct a packet to submit. This packet creates a callback that handles this creates a closure callback that handles the non-closure native callback. It converts the payload from a raw pointer to a Rust box, an owned pointer. The payload is a U128, a box of U128. And the packet converts again to a box. This result we copy out of the result pointer, so we don't hold those raw pointers. Then we just send it all back. And this code, confusingly runs after the next code. It's a callback for use later, but that is This is still not finished. All this block is constructing a packet. So this is one of the nice things you can do in Rust is you can put everything you want inside some kind of scope. Create scopes everywhere. So all this is involved in constructing a packet. I'm already pretty confident about this packet. The account is the payload. Is that true? Yes. The account is the payload. We put that into data. Next pointer is null. This is used internally by the client. I don't need to deal with that. I also learned, chat, from other Tiger Beetle people that all this batch stuff is just internal fields used by the client. I don't even need to think about it. All the batching is done by TB client directly. The bindings don't need to worry about batching, which is very convenient. All right, our user data, though, is our callback, double boxed. Lookup accounts is our operation. We set the status to OK. Mem reserved is nothing. Okay, we submit the client. And then after submission, we get on completion is called, and all that does is convert the user data into a Rust boxed closure, double boxed closure, and then it calls the closure. Easy peasy. Which runs this callback and sends this message that we receive. And we take out the packet and we take out the result, which are the two datums that we care about. The packet, if the packet status is not okay, we still got all of our heap data boxed again. It's going to get deallocated correctly. Asserting something we think we know about the result, converting the result into the ops specific result and handling it. This all looks good. Looks good. Okay, so next thing I want to do is write a little test of it. Not a real test, but just write a little program to exercise what we've done so far. And this all has to be async now. Oh, chat, I'm sorry I did not clue you in with the code I was looking at. That is a bummer. I'm always forgetting to switch scenes. It's in the past now. You just gotta forgive me, I suppose. But we're gonna have to do some async code to exercise this. We have to initialize an async runtime to exercise this code we've just written. So I'm going to go over to our browser, and this futures crate contains some kind of really simple executor, and I'm wondering if I want to go figure it out or if I want to just use Tokyo. And probably the thing to do is just use Tokyo. But to do that, I'm going to have to go read the Tokyo docs. I don't really know how to use Tokyo offhand. And I'm going to go look at, well, actually, chat, we can go at least add Tokyo as a dependency. Let's go back over to our code. And we're going to say cargo add Tokyo. And again, it's just a dependency of our test binary here. This is not a dependency of our Tiger Beetle library. Our Tiger Beetle library is going to be agnostic to Rust async runtimes. Oh, I have just really screwed up the window here. Let me get that back in order again. I have also forgot to turn off my background music. A lot of screwing up tonight, chat. My bad. My bad. Yeah, I wanted to see what cargo add did. You can see lots of features in Tokyo. I think we don't need any Tokyo features. We really just need to get inside of an async runtime. And I know there's some kind of Tokyo annotation to do that. So let's go back over to our browser. And just read the docs for a second. Oh, it's that. That's the whole thing. So we need to say Tokyo main, make main async, and then we got to block on something or await something. Have to have some future to await on, but we will have one once we submit this operation. Okay, that seems straightforward. Let's go back to the code again. And we probably have to say use Tokyo. I am not actually sure. Their example did not do that. I feel like we can't possibly use this attribute without importing it though. Let's just cargo check that and see what that does. Yeah, no Tokyo en route. Can we really just use that attribute? No. Maybe some feature we need to turn on. Oh, it's Tokyo main. That's why. This attribute is not Tokyo. It's Tokyo main. Could not find main in Tokyo. So I am reading the docs and I'm not showing you the docs. I'm just trying to figure out. There's some feature we have to add to Tokyo to make this work. And I'm thinking I'm just going to add the full feature just to not worry too much about it. So if we go to our, whatever this is called, manifest, you can say, I think this is called version. Can't be right. Maybe it is. Features equals full. And we'll see if Tokyo likes this version or not. It did. Async function main needs to be async for a Tokyo main. And that should run. Yep. And now we can say use Tiger Beetle as TB. I just want something short to type. And have to go remember how to use this API we've created. We're going to say let client equals client new cluster ID. And then some address. And oh yeah, we got to run a server. So I'll go over to this window here where I keep my test server. I already have a test database formatted here. We did that last stream or some other stream. And I've still got it sitting around. Okay, so our server is running. And this client, just creating the client is not gonna do anything, but let's run it and make sure it doesn't panic at least. That's a TB client new. Yep, okay, works. And then the only other thing here is submit account lookup of an account lookup operation. So we're going to say client.submit account lookup TB account lookup operation. And that has a field called account 1. Because remember, our assumption is that 0 is not a valid account. And this returns a future. So we can say let result equals this account lookup dot await. And this is a result of account lookup OK. And this result is, this will return an error for, I think it's for like bad errors. If we actually connect to the server and get something back, this should not return an error. So I'm just going to question mark that error away. But to do that, I'm going to need to make this return a result of something. And we're going to have to import anyhow result for that. And so that's pretty cool. Yes, that is how you want some async Rust code to look, right? So we made a good looking Rust async API. And then we can just print whatever this result is. This result is an account lookup OK. We might as well go put a derived debug on that so we can easily print it. And result is, how do you do this? Result, I think that's the syntax. Feeling a little bit nervous. This is where the rubber meets the road. Where the rubber meets the road is compilation errors. That's where the rubber meets the road. What did I do wrong here? Method not found in that thing. So TB client new could return an error. So let's question mark that error away. And still have, okay, function should return a result or option. This function should return result or option to accept question mark. Is it not possible to return a result from a Tokyo main function? Does Tokyo main not like this result return type? That seems surprising. I kind of don't want to go do a bunch of research about how to use question mark in Tokyo main. Although maybe the thing I'm screwing up is just this OK at the end. Maybe type inference has screwed this up. I think that's the case. Okay, that was a pretty nasty error. But in fairness to the Rust compiler, it's really the problem with how Tokyo main is defined. You can see that Tokyo main puts your code inside of an async block. And then the result is that because I didn't put this OK at the end of the block, I saw some errors up here. Pretty gnarly, not good stuff. Okay, cannot borrow as mutable. That's fine. So I've said these methods are mutable on client. Private field, that's easy peasy. Make that field pub. I'm gonna run and okay, something did not work here. I bet I know what that is. Where is that assertion? Line 118. In lib.rs, not in that, in lib.rs. Yep, it's that. So I was wrong about what the result pointer means for this operation. And that's fine. It's easy to fix. I also want to point out that this printed completion. I have some little debug logging inside of this on completion. Now we've seen it work. We can just delete that. All right, so I was thinking, you can see the assertion left, right, 0, 16. Good thing I put this assertion here. I wrote this assertion. I was not sure about this, so I put the assertion there. So for the account lookup op, every op has a different result, different interpretation of result, and I've interpreted result incorrectly. Which this is very interesting because the result is 0 here. The length of this is 0. I'm kind of wondering, up here I boxed it. This result lin is probably 0. So I'm going to say, and I'm wondering if this result pointer is 0 or if this result pointer is pointing to something. This result lin should be 0 though. I'm kind of expecting that I'm allowed to convert this result to a vec all the time, that the Tiger Beetle client will not just put junk in this pointer. But anyway, in this case, at least where I did not find the account I was looking for, this result was empty. So this is making me think, like, if I find the account, is the result a U128 containing that account again? And if I don't find the account, the result is just unallocated, a pointer to nothing. Is that how this operation works? That's my new hypothesis. Anyway, let's go turn on the REPL and add an account here and see what happens when there is an account. Okay, so we're going to say zig build run REPL, and I'll just ask it to tell us the arguments. Addresses equals 127.0.0.1. Cluster equals 0. I'm looking over here at our server logs, and you can see the server did get a connection. So that's great. So our client is at least talking to the server. And here we can say create accounts, and I'm just cribbing off of this help message here. ID equals 1, code equals 10, ledger equals 700. Look up accounts, ID equals 1. Okay, so now we have an account, and we can go run this and see. I'm going to print what this result is. So I'm hoping this result actually contains a U128 now. Then I'm going to print it. The result here, okay, this is so much weirder than I expected. So the account exists now. Oh, my heart. We're looking up an account, right? We're not just asking. I'm so embarrassed. I'm so embarrassed with myself. The name of this operation is lookup account. So if we look up an account, we expect to get a description of that account, not just a 128 saying, here's the ID of the account that you just handed me. We expect to get some kind of useful information about the account. And so I've been assuming for some reason that, like, our payload for lookup account is a account ID, and the result of lookup account is also that same account ID, which is dumb. That doesn't make any sense at all. Ooh, okay. So you can see here from the assert failure here that the result when an account is found is something that is 128 bytes. And this should be pretty easy to figure out what that is. If we go look at some of our definitions, probably if we look in tbclient.rs, there will be a struct here that represents what's in an account. Struct. There you go. There's an account. Okay, so we looked up an account, and it's this. And I'm thinking about whether I want to fix this tonight and how to fix it, or if we want to sleep on it. And the reason I'm thinking about sleeping on it is because, we have to convert that result vec to this. And in Zig, the way Tiger Beetle is going to do it is just going to do a cast from a pointer of bytes to a pointer of TB account T. And I don't want to do that. That's not how you do things in Rust. Maybe I'll just do it. I'm just wondering if there's any kind of Rusty abstraction that boils down to doing exactly that without actually open coding cast from a pointer to a buffer to a pointer to a struct. Maybe though, let's at least do it the super unsafe way for now and maybe come back to it. So let's go ahead and create this, get this struct. Unfortunately, this struct already implements debug too. So what I think we're going to do is account lookup operation, account lookup OK. It's either found or not found. And if it's found, this could also be like an option. If it's found, it's going to be an account. Now this is kind of like one of the core Tiger Beetle types here. For now, I'm just going to reuse this TB account T. But in the real Rust API, I'm not going to expose TB account T directly. Like you could, and it would be fine from a type perspective, but from a generated docs perspective, I don't want users to see any of this garbage. But for now, I'm just going to say, if it's found, you get this. You get the thing from the bindings. And here, this is all wrong. I'm going to say this assert EQ, say if result.len, result.empty. That's the not found case. We're going to say return OK, account lookup OK, not found. And again, we could just make this case be a none. You found a none. And that's probably the thing to do. If this is a none, yeah, it's just all going to be a future fix me. This function is going to return, eventually it's just going to return an account. But for now, it's going to return a not found. Okay, so this code is incorrect. This code is incorrect. Just all incorrect. So if it is found, though, the size of this result is going to be the size of TBC TB account T. I believe that is the case. These tiger beetle core types are all carefully designed to be packed and fit exactly into a very specific amount of memory. And within tiger beetle, there's no serialization generally, as far as I know. This is just going to be cast straight to a buffer. And for now, I'm going to say let, we're going to have to have some unsafe code here again. Get rid of all of this. None of this is useful anymore. Let account, and this is going to be a pointer to a immutable TB account T equals result.as pointer. I think this is a method on a slice that'll give us a pointer. As star, oh, duh, this is not correct in Rust. Star const, as star const TB account T. And then we can just say return return OK of, sorry, my brain is slowing down. It's been a while. Been streaming for a couple hours now. Account lookup OK found, and then we copy account. So we dereference account to get a copy of it. Let's see if that checks before we dare run that. Oh, wow. Lots of complaints from the compiler, huh? Oh, didn't name everything correctly here. TBC. Empty is wrong here. This is empty. Okay. I put an EQ on account lookup OK. So I, on my result here, put EQ and partial EQ, but over here, the thing that's inside of it does not implement those. So I don't even need these for now, at least. So I'm just going to get rid of them. Okay, that checks. Let's go look at our main function again. Okay, so we're just printing this result. So we should, if this gets here, we should see it print this big old struct, which should be nice. And there it goes. It's pretty printed. I mean, it printed it, but it wasn't pretty. So I'm going to go see. I think that is the pretty print syntax. There we go. Oh my gosh, chat, we did it. We created an account, and then we wrote a Rust API that uses the TB client bindings to talk to Tiger Beetle and get the account. And that is the whole account right there. You can see it. You know, it's not all pretty yet, but we accomplished the thing. And now we have a roadmap for all the other Tiger Beetle operations. Just do it like that, but with slight tweaks for every single possible operation. Seems pretty straightforward from here out. Modulo a lot of polish and etc. Now I'm going to put a big fix me here because, you know, the way we did this, and I mean, the way it's intended to be done is we cast the result buffer directly to this TB account T type. And like, if you really know what you're doing, you can do that, but it's pretty unrusty to just cast bytes to a Rust struct. I'm not liking this. Can this unsafe cast be done more rusty? So what I'm thinking is there's probably some Rust crate that encapsulates this whole concept. So like if you're a little Indian architecture and you define your struct perfectly, you understand the layout, you can just say, yeah, okay, the struct is actually reinterpreted as just a bunch of bytes and vice versa. That's something you can do if you really know what you're doing. Also, your alignment has to be perfect. And it works here. And this is the way it's intended to be done in the Tiger Beetle and the way the Tiger Beetle API is defined. But in Rust, I would never do this. I would never do this in Rust. And so I'm wondering if maybe there's another crate that kind of encapsulates this concept. Like, for example, there's a serialization crate called bin code. I don't think bin code is this, but it's kind of a very simple serialization. And I'm wondering if there's some serialization crate that is like, we don't actually do serialization, but it looks like serialization by just doing a buffer cast. So I'll just put a fix me here and deal with it some other time. Like at least I would want to say like, assert this is a little Indian architecture. Like I think that's kind of the very minimum you need to do for this to possibly work, is you got to be on little Indian. If there's a big Indian, then your non-byte numbers are just going to be all jumbled up. Anyway, I'm feeling great about this, chat. We made so much progress recently. So I'm gonna, oops, what did I just do? Wrong window. I'm gonna push this. And yeah, so next time we're gonna leave this fix me here because, you know, whatever, it works. We should probably fix this close function to do the correct thing. So next time we'll probably fix close, make close work correctly. And then go ahead and implement at least one more operation. And then after we have things working, we really need to think about how to test this. And we'll definitely have to write some unit tests at some point. Or actually, there'll be really more like integration tests because we got to spin up an entire server to make the test work. And Tiger Beetle has a new testing system called Vortex. I assume that's public. I hope that's public. That I believe I can wire this into. That I think is capable of just testing the client from the command line. So we'll just start thinking about testing this soon. But probably the first thing to do is just implement the rest of these operation types. And man, we're going to be good to go. It's going to be ready to actually use, not this week for sure, but if we move fast enough, maybe other people could use it in 2 weeks, perhaps. Okay, chat. This has been super fun, super productive. If you've been hanging out and paying attention to what we're doing, I really appreciate that. That means a lot to me. We're streaming the same project for a few weeks still. Well, until this project is done, every bit of this project I'm going to stream right here. Don't have a regular schedule, but perhaps I will set aside some time in the schedule to consistently be here. But I'll be here on and off pretty frequently for a while, just streaming about this Rust client. That's it. I'll catch you next time. Thanks a lot.